Welcome back to the next video, everybody. Today we're going to keep pushing towards proving R equals T in the general case, and we're going to obtain our first serious proposition along those lines in this video. So first, some definitions. M is going to be a finitely generated free R module over our ring R, if you like commutative unital ring. Let N0M denote the sub-RG module of NM, so endomorphisms of M, consisting of trace zero endomorphisms. We'll let rho from G to GLD of R be a representation of some group G, and we'll let M sub rho denote the underlying RG module, which means another way of saying that is M rho is isomorphic to R to the D as R modules, and then there's a G action on M rho. Let's set add rho equal to end M, and we'll set add zero rho equal to N0 M rho. Note that add rho is isomorphic to add zero rho direct sum R, where R has the trivial G action. This is a quick exercise. More definitions. Throughout this chapter, O is going to denote the ring of integers of some finite extension of QL, where L is some typically odd prime with a residue field K, and lambda will be the maximal ideal of O. We'll let G sub L denote G sub Q sub L, thought of as a subgroup of G sub Q, so it's a decomposition group at L. We talked about all that back in chapter 1. Okay, more definitions. So let's let L be an odd prime. If M is a profinite OGL module, let's make the following definitions. We'll say M is good if every discrete quotient of M is isomorphic to F Q bar L as ZL GL modules for some finite flat group scheme F over ZL. Okay, so this is like a flatness condition. Although, well, I'll get to that in a second. 2, M is ordinary if there is an exact sequence 0 to M to the epsilon to M to the end of the first to 0 of profinite OGL modules such that inertia at L acts trivially on the last guy, hence the 1, and by the L-adic cyclotomic character epsilon on the first guy, hence the epsilon. Okay, so we have a trivial inertial line and a cyclotomic inertial line. And then we'll say that a representation rho from GL to GL2 of O mod lambda to the n for some n with cyclotomic determinant is semi-stable if M sub rho is semi-stable. And what does it mean for M to be semi-stable? It just means it's good or ordinary. Okay, so that's what I was going to say is like this goodness condition isn't necessarily just flatness, but it's flatness plus cyclotomic determinant. Okay. All right, so if I give you a semi-stable representation rho from GL to GL2 of O mod lambda to the end, we're going to need to define O submodules inside H1 of GL add rho. So this is like Galois cohomology here. And those submodules are going to be called H1SS and H1F. Okay, so how do we define those? Well, let's do that. Let's let G be a profinite group, and we'll let rho from G to GLD of O mod lambda to the n be a representation of G. Recall from chapter 4 of the playlist that there is an O mod lambda to the n linear isomorphism, H1G add rho with extensions of M rho by N rho in the category of O mod lambda to the n G modules. Okay, it's not hard to check that classes in H1G add zero rho, so replace add rho by add zero rho. Where do those correspond to here? Those correspond to equivalence classes of representations rho prime with determinant det rho. So it's a fixed determinant condition. I think we actually proved this in chapter 4. Okay, so what are these special submodules? Let's return to our semi-stable representation rho from GL to GL2 of O mod lambda to the n. And we'll let H1SS GL add rho be the image of H1 GL of add rho of X M rho taken now in the category of semi-stable O mod lambda to the n GL modules. So we're not looking at all of these modules. We're now looking at semi-stable. We're looking at the category of semi-stable modules. We're going to extend by semi-stable modules. Okay, so that SS stands for semi-stable. Okay. All right, how about H1F? Well, if rho is not good, we'll define H1F to just be H1SS. No difference. Otherwise, it's going to be the natural image in H1 GL add rho of X M rho again, just like it was up here, except this time we're going to look in the category of good O mod lambda to the n GL modules. So F stands for flat because we're looking at good extensions. Okay. How do you like define all this stuff on add zero rho instead of on add rho? Well, we'll let H1F GL add zero rho just be H1F GL add rho, the full thing, intersect H1 GL add zero rho. Make an analogous definition for H1SS on add 0 row. Okay. What about if we want to like tensor up to K mod O? What are the definitions then? If rho from GL to GL2O is semi-stable, we'll set H1FGL add rho tensor K mod O. That's just going to be the direct limit of H1 of FGL add rho tensor lambda to the negative n mod O. Okay. And this is, of course, sitting inside H1GL add rho tensor K mod O. Okay. How about if we want to tensor up to K mod O, but look at add 0 instead of just add? Make the obvious definition. So H1FGL add 0 rho tensor K mod O is just going to be H1FGL add 0 add rho tensor K mod O intersect the full H1GL add 0 rho tensor K mod O. Defined H1SS or tensor up to K mod O and H1SS tensor up to K mod O trace 0 similarly. Do the exact same thing. Okay. So here's the first key proposition that we're going to need. All right. This is the beginning of R equals T in the general case, I would say. 3 parts. Part 1. Suppose rho bar from GL to GL2 of K is semi-stable. Then the cardinality of H1F GL add 0 rho bar is the cardinality of H0 GL add 0 rho bar times the size of K, the cardinality of K. Okay. 2. Suppose that rho from GL to GL2 of O is good and ordinary. Let chi1, chi2 be the unramified characters such that rho is kind of behaving like chi1 epsilon star 0 chi2. This is coming from the ordinary definition. Okay. Now we're going to let CL be chi1 over chi2 for Frobenius L minus 1. If CL isn't 0, then H1SS of GL add 0 rho tensor K mod O over H1F GL add 0 rho tensor K mod O is finite. And in fact, I can tell you the order. It's the cardinality of O mod CLO. Okay. And finally, 3, if rho mod lambda is either not good or not ordinary, then H1SS GL add 0 rho tensored up to K mod O is the same as H1F GL add 0 rho tensored up to K mod O. Okay. So proof, part 3 is an exercise in definitions. I'll leave that to you. For parts 1 and 2, we'll need 3 lemmas. So lemma 1, we'll let L be an odd prime. We'll let A be a complete Noetherian local ring with residue field K of characteristic L. And I believe L has to be odd here. I could be wrong about that, but it will be for us anyway. And let rho from GL to GL2 of A be a good representation. Then, first of all, there is an injection from H1 of like unramified classes. So H1 GL mod ILA into H1 FGLA. But furthermore, not only is there an injection, this injection is an isomorphism. Okay, in particular, and this is a quick little exercise, the cardinality of H1 FGLA is just the cardinality of it. Okay. Lemma 2, this is Fontaine's work. So when you hear about Fontaine in the proof of Fermat's theorem, this is the part that they're talking about when people say that. Although he kind of gets involved at a couple other points, but this is the main part people are talking about. So 2, suppose that rho from GL to GL2 of O mod lambda to the n is good, then the cardinality of H1F GL add rho is the cardinality of H0 GL add 0 rho times the cardinality of O mod lambda to the n squared. Okay, and then lemma 3 is a result of Wiles. It's a kind of just a technical computation. Suppose that rho from GL to GL2 of O mod lambda to the n is ordinary, then 2 things are true. First of all, cardinality of H1SS GL add 0 rho is at most the cardinality of H0 GL add 0 rho times the cardinality of O mod lambda to the n times the cardinality of O mod the ideal generated by lambda to the n, and that's C sub L from earlier. And if rho is good, this is actually an equality. Okay. 2, if n equals 1 and rho is not good, then the cardinality of H1SS GL add 0 rho is nothing but the cardinality of K. Okay. I'm going to prove the proposition assuming the lemmas in this video. Let's deduce proposition 1, part 1 in the good case first from the lemmas. So let's assume rho bar is good. We'll recall that K is a direct summand of add rho bar in the beginning of the video. By definition, H1F GL add 0 rho bar is the kernel of the trace map or the map induced by trace, whatever. H1F GL add rho bar to H1 GLK. By lemma 2, the domain of this map has cardinality, the cardinality of H1F GL add rho bar, which by the lemma is cardinality of H0 GL add 0 rho bar times the cardinality of K squared. So it suffices to check that our map here is not the zero map because it's a k-linear map. So check that it suffices to show that. That's an exercise for you. That's a little basic linear algebra exercise, essentially. Okay, now rho bar is good. So let's go to lemma 1. Lemma 1 basically consequence is that the unramified classes here, H1 GL mod ILK, those actually have to live in H1F GL add rho bar intersect H1 GLK. The unramified H1 is not zero. We proved this back in chapter 4. I think we called it lemma 1 back then. Well, that means the image is not zero because it contains a non-zero group here, as desired. Okay, so that's proposition 1-1 in the good case. Well, sorry, it's the inequality of proposition 1, part 1 in the good case. How do we get the equality? Use the isomorphism of lemma 1 to find that the image of the map H1F GL add rho bar to H1 GLK has size the cardinality of K, not just at least the size cardinality of K. Then use the first isomorphism theorem. Okay, so I'll leave the details to you. Okay, how about proposition 1, part 1 in the good, not good, but ordinary case? The inequality follows immediately from part 2 of lemma 3 and definitions. I'll leave that as an exercise. And then we want equality, though. Equality will follow if we can show that H0 GL add 0 rho bar is trivial. Check this. Check that it suffices to show this. That also follows essentially from definitions and the lemmas. Okay. So how do we do that? Well, first, let's note that if rho bar is split, then it must be good by Raynaud's equivalence of categories from the end of chapter 5. If you want to see that a little more concretized to this specific setup, you can see lemma 2.22b in the Diamond-Darman-Taylor notes, or even more broadly, theorem 1.6 on page 383 of Cornell, Silverman, Stevens. We'll actually return to this result later. Okay, but we're trying to assume we're in the not good but ordinary case. So this tells us we can assume rho bar is not split, so it's not a direct sum of representations, and we can assume it's ordinary because that's what we're doing. Okay. Let's note that M rho bar, so the representation space, has a unique line M epsilon stable under Galois with unramified quotient M1. Let's let phi and M end of M rho bar be a non-zero Galois equivariant map. Then phi is an isomorphism, actually, it turns out, just by being a non-zero Galois equivariant endomorphism. The reason for that is, otherwise, the kernel and the image of the map would be lines. Well, then they would have to be M epsilon because we're not split in Galois equivariant. So that's a quick little exercise. So phi is a non-zero Galois equivariant map from M1 to M epsilon. Well, I mean, that obviously can't be true. This is unramified. This is cyclotomic. Okay. All right. So let's suppose that phi is not similar to a triangular matrix over K. Then phi is in a non-split Cartan in M rho bar. That just means it's diagonalizable over a quadratic extension of K, but not K. Also check this. As a hint, there are 4 conjugacy classes in M2K in this case. It's not hard to rule out the others. Okay, and M rho bar is contained in the centralizer of phi by Galois equivariance. That's another quick exercise for you. This centralizer is exactly the polynomials in phi. Again, another exercise for you. This is where we're using that phi is in a non-split Cartan, and it's just really a little linear algebra exercise. Okay, since rho bar is ordinary, every element of M rho bar is similar to a triangular matrix and to a polynomial in phi. But then phi has to be scalar, right? Because we're assuming phi is not similar to a triangular matrix over K. So I mean, basically what would have to happen here is that phi would have to be like a scale, it's similar to it, like it'd have to be a scalar polynomial. So scalar, okay. But that's a contradiction, right? Because if it was scalar, it would definitely be similar to a triangular matrix over K. Okay, so contradiction. So phi is similar to a triangular matrix over K then. As a result, phi has an eigenvalue lambda. So if you look at phi minus lambda times the identity, this is a Galois equivariant singular endomorphism, and so it must be 0. So that proves this group is trivial here. That's what we wanted. Okay. As for the second part of proposition 1, it immediately follows from lemmas 2 and 3 in definitions. I'll leave it as an exercise. Okay. Just a quick remark. We're going to prove the 3 lemmas in future videos. Actually, we're going to prove 2 of the 3. And then Raynaud's result that we used, remember, that was proven in chapter 5. Okay, so next video, I will prove lemma 1 for you. So I'll see you then. Thanks for watching.